Good day, everyone. We're reviewing Wetzel's Limnology textbook, edition number 4, and we're in chapter 7, which is Fate of Heat. And more specifically today, we'll be looking at annual patterns of stratification. Classification schemes describing stratification in lakes are based on the frequency of circulation occurring throughout the entire water column on an annual basis. Patterns of stratification and mixing vary with local or regional differences in climate combined with lake-specific factors such as differences in morphometry, exposure to wind, and radiation and chemistry. Classification schemes were developed by Forel, who is often referred to as the father of limnology. His extensive monographs on Lake Léman, Switzerland, in 1892, 1895, and 1904 served as a foundation for limnology. Subsequent classifications were developed and further refined. Here we distinguish annual stratification patterns, in which the patterns are generalized by latitude, altitude, and depth. Lakes at far northern or southern latitudes that are ice-covered year-round and do not fully circulate are classified as amectic. Lakes in which complete circulation occurs at least once a year, or at least in which stratification throughout the water column becomes quite weak and at some times during the year, are called holomictic. Holomictic lakes are further discriminated by the number of periods per year in which the lakes are classified as circulating or mixing on the basis of near isothermy. Higher resolution instrumentation indicates that stratification is often present in such periods and that mixing throughout the water column is intermittent. That said, on the basis of near isothermy, monomictic lakes have one period in which water temperatures are near isothermal. Dimictic lakes are those with two such periods, and polymictic lakes have more than two such periods. Cold polymictic lakes have ice cover in winter, whereas warm polymictic lakes do not. We remove the distinction between continuous and discontinuous polymixes, which had been distinguished on the basis of fetch, the length of the lake along the axis of prevailing wind. Recent analysis indicates that even small lakes may stratify for periods of several days, and that the apparent mixing at night may be the result of thermocline tilting. The depth dependence illustrated in figure 7-32 is not precise. For example, both Lawrence Lake and Lake N2 described above are 10 meters deep, yet both are dimictic. Curlin and Shotwell provide approaches to predict whether lakes will be polymictic or stratify seasonally based on depth, optical properties, and mean Mornin-Obuchov length scale. And Shotwell link within and between year changes in classification type to seasonal changes in algal biomass due to zooplankton grazing. So before we move on, let's look at this figure here. So on the x-axis, we have the latitude, and from pretty much the North Pole, 90-degree latitude, to all the way to the equator at 0 degrees. And then here on the y-axis, we have the lake depth in meters. So what we can see here is, for example, like up to 75-degree latitude between 90 and 75, we have amectic lakes. And usually those are frozen the entire year. Then we have between 75 and about 40-degree latitude, we have three types of lakes. So the shallower lake are called polymictic lake. The one that have like a pretty good spread in terms of depth between 100 and mostly 40 meters depth, they are called polymictic. And then we have dimictic lakes, and that share increases as you move toward the equator. And speaking of the equator, between 40 degrees latitude, and which would be, somewhere around Northern California, and the equator, we have two types of lake. We have the warm monomictic lake when they are deep, and then the warm polymictic lakes when they are shallower. Although we are seeing an increase in share of the warm polymictic lake as you are approaching the equator. There are two other stratification types: oligomictic lakes, undergo full circulation of the water column in intermittent years, and meromictic lakes do not undergo full mixing due to their great depth and or presence of a chemocline, which further increases the density stratification and the difficulty inducing mixing. In the following further details and examples are provided for lakes in each classification scheme. So there is a term here that has not been defined, which is the chemocline. So think of the thermocline as being an abrupt change in temperature over a short depth. And a chemocline is the same but applied to chemistry. So therefore, in a chemocline, you have a change in the chemical composition of the fresh water over a short distance or a short amount of depth. Amictic lakes. Lakes defined as amictic are sealed perennially by ice from most of the annual variation in temperature. Amictic perennially ice-covered lakes are rare and largely limited to Antarctica and the high Arctic, or more rarely to high mountains. That said, with ongoing climate warming, some of the lakes in the high Arctic are beginning to open with only a small amount of residual ice in summer, while mixing is expected to be enhanced in lakes that continue to be amictic. With ongoing climate change, these lakes, which have been amictic, may even shift to cold monomictic. Few amictic lakes have been recorded in the Arctic, mostly in Greenland and Ellesmere Island in Canada. As elsewhere, conditions necessary for the formation of a permanent ice cover are rare. Heating of these lakes depend on light penetrating through the ice and absorption by pigmented microbial communities. The balance of heat inputs and losses tend to be relatively constant over annual cycles. While these lakes do not fully mix, they can have complex thermal structure due to the combination of thermal and chemical stratification and horizontal convective circulation due to lateral heat inputs or losses. In summer, with the melting of ice on the margins and stream inflows, additional mechanisms for advective exchange can occur. Microstructure data indicated low levels of turbulence in exchange flows between basins. Cold monomictic lakes. Lakes with water temperatures equal to or below 4 degrees C, ice covered most of the year, and with only one period of circulation in the summer are described as cold monomictic lake. The category comprises, for the most part, Arctic and mountain lakes, which are ice-free for brief periods in the summer and may be in contact with glaciers or permafrost. The thermal cycles of Arctic lakes have large variation in relations to their location, depth, and summer climates, such that not all are cold monomictic, and the stratification type can vary between years. Lake Schrader in the Brooks Range in Alaska was dimictic and stratified in 1958, with a temperature in the epilimnion of 10 degrees centigrade and the hypolimnion of 4 degrees centigrade. The following year, summer ice breakup occurred a month later, and the lake did not warm above 4 degrees C, that is, it was cold monomictic. Broadening the temperature range for classifying cold monomictic lakes may be appropriate given the small changes in density above and below 4 degrees C. For example, Clear Lake on Cornwallis Island, Canada, at a latitude of 76 degrees, warms to between 4 and 5 degrees C, and is technically dimictic, but does not always stratify in summer. Cold polymictic lakes. Mixing occurs more than twice per year in polymictic lakes. Cold polymictic lakes differ from warm polymictic lakes in that they are ice covered for part of the year. When ice-free during the warm season, temperatures may be close to 4 degrees C, as in nearby cold monomictic lakes, but even at the most northern latitude, due to their shallow depth, they may warm to temperatures above 4 degrees C, such that they stratify. Mixing can occur due to heat losses and wind at night or after cloudy periods. Besides some Arctic lakes, many shallow north temperate lakes have this circulation pattern. Cold polymictic lakes are also found at higher altitudes in equatorial regions with high winds and low humidity, and where little seasonal change in air temperature occurs. At high altitudes in equatorial regions, cold polymictic lakes gain a significant amount of heat during the day, but until recently, nocturnal losses were insufficient to permit mixing during the night. Although shallow polymictic lakes are assumed to mix on a near daily basis, or at least frequently, interpretation of high-resolution time series data using metrics such as the lake number indicates dynamics are more complex. Strong near-surface stratification built up in Lake Saint-Augustin in Quebec during morning heating, and the mixed layer deepened with afternoon winds as LN dropped to 1 or below. The return of cold water in the lower water column at night when winds decline indicates that the apparent mixing was the result of the upper mixed layer downwelling at the measurement site in the day. Thus, on many days, the lake had not fully mixed despite near isothermy in the afternoon. Lake Essex in subarctic Alaska provides an example of a shallow lake with brief periods of stratification. Lake Essex has a surface area of 0.0019 kilometers squared and is 3 meters deep. Depending on the year, periods of stratifications persisted for several days, up to 10 days. Thermoclines developed in these periods with buoyancy frequencies higher than in the larger nearby lakes. So before we move on, let's look at figure 7-33 here. So this is isotherms over an annual cycle for cold polymictic Char Lake in Nunavut, the dimictic Toolik Lake in Alaska, and then the meromictic Ace Lake in Antarctica. So the first one is Char Lake, Nunavut. So what we see is on the x-axis we have the month, and on the y-axis we have the depth, and the hashed area here is ice. And so therefore, like right around July, August, we have a pretty uniform temperature profile in the lake. We don't have a thermocline. And then we, at the onset of ice, we have therefore a development of a thermocline, which is the case as well here until the ice melts. The same kind of scenario here, but a different layout of the data here. So this is for Toolik Lake. So Toolik Lake, this is the ice layer when ice is present. And here we have July through July. So rather than November through December. So therefore, like in July, we have development of a thermocline, then the erosion of the thermocline, the presence of an ice cover, and then the inversion of the thermocline, so warmer temperature at the bottom compared to the top. And then with the melting of the ice over the surface of the lake, we have the development once again of a thermocline. And this lake, the last one, is lake in Antarctica. So here we actually have just one opening here, where so this lake cannot be amictic because it appears that we have an area here like it would be in February where it's ice-free. And otherwise, the lake always has a thermocline. And what is interesting here is we have temperatures that are below the freezing level. So for example, -1 here, you would expect that the ice has developed, and probably what happened is that that water may be saline, may have high TDS and prevents it from freezing. So here we have the development of a thermocline, and we actually don't have, like it appears, an inversion. So the temperature decreases as you are reaching the bottom of the lake, and that's about it. Let's see. N reached 55 CPH around DOY 190. So all of this is a description of the figures we just went through. Why don't we go into dimictic lakes? Dimictic lakes are prevalent in subarctic, boreal, and temperate regions of the world where ice forms in winter. Their characteristics were described above and illustrated for spring through autumn. So let's see. This is a time series for Lake Saint-Augustin in Quebec. So this is probably a lake located in the boreal region of Quebec. And so here we pretty much has the same pattern of graphs than we did before. We have the wind speed here, meters per second, the lake number, the depth, and then so the depth for temperature, and then we have the buoyancy, the N value here in CPH. So, and then we have 28 June through 16 July. So this is pretty much like a summer-based temperature profile. And you can see that we have heating events of the water surface. It's actually a very shallow lake. So it's a 4-meter deep lake. And then we have therefore the presence of a thermocline, but then in the absence of this heating event, we have the erosion of a thermocline, and the pattern of the buoyancy factor follows that as well. Okay, let's see here. Our understanding of dimictic lakes has been altered with the use of high-resolution instrumentation. The term dimictic resulted from the assumption that lakes were freely circulating in autumn and spring and assumed to be mixing, in contrast to being more stably stratified in summer and winter. In fact, some stratification is also present in autumn and spring, albeit weak, and interrupted by periods of mixing. Mixing periods are often ones in which the stratification support large internal waves where water both upwells and downwells with respect to temperature stratification. Dimictic lakes are stably stratified when temperatures are above the temperature of maximum density, which when solute concentrations are low, is precisely 3.98 degrees centigrade for 4 degrees, and inversely stratified when temperatures are below this value. Thus, density stratification can be stable in autumn prior to the ice on, yet temperatures can be inversely stratified under the ice in winter. Temperatures are often inversely stratified, but as ice melts and snow melts, flows into the lakes in spring, freshening near-surface waters. Near-surface temperatures can reach 8 degrees C. Stable temperature stratification can occur in the dilute near-surface boundary layer, and inverse temperature stratification can persist below where solute concentrations are higher. So this is for Lake E6 in Arctic Alaska. So here we have your shortwave radiation value, so watts per meter square. We have the heat flux, the lake numbers, the depth and temperature profile, and the depth and the buoyancy factor. And this is number of days, so we have like about half a year. So from like July to, like late June, July, all the way to like early January here. So with the development of ice, as we know, we have erosion of stratification. We do have stratification during heating events right here with the development of a thermocline. The white dots probably means that there is ice off for that time, although it doesn't indicate when the ice is coming back. And so that's, I'll let you review that further. And let's see here. The duration of autumn cooling and the onset of ice formation in dimictic lakes varies between lakes and depends upon basin morphometry, the volume of water cooled, and prevailing meteorological conditions. For example, Lawrence Lake, with a surface area of 0.05 kilometers square and a volume of 0.29 by 10 to the 6 meter cube, cooled to and below the temperature of maximum density by early December. Waters of nearby Gull Lake in Michigan, with an area of 8.27 kilometers square and a volume of 102 by 10 to the 6 meter cube, usually circulate well into January before reaching comparable temperatures. Large lakes such as the Laurentian Great Lakes, which are of similar latitudes of the Gull and Lawrence Lake, circulate all winter, and depending on latitude, may only have ice cover in near-shore region. In large deep lakes, for example, 450 feet deep Great Bear Lake of the Canadian Northwest Territory, late summer circulation often does not extend to the lower depth, because stability is sufficiently strong to prevent mixing. The temperature of the maximum density of the water below 200 meters is 3.53 degrees centigrade because of the hydrostatic pressure. In cold years with slow spring heating, when the upper 200 meters of water are cooled to 3.53 degrees centigrade in the autumn, the upper waters reach the same temperature of maximum density as the water below 200 meters. Circulation then extends near the bottom. Changes in mixing patterns in Lake Michigan over the last 75 years are described by Anderson and Cannon. Quantify the turbulence both as the rate of dissipation of turbulent kinetic energy and the coefficient of eddy diffusivity in the upper 55 meters during summer stratification. The convective period in winter and spring when both are much higher, and the transitional periods in between. Dymictic lakes are expected to mix near ice off as near surface temperatures reach the temperature of maximum density and exceeds those below, leading to mixing throughout the water column. While the density stratification under the ice can be weak, solid production by respiration and the flow of gravity currents can lead to near bottom chemoclines and pycnoclines, regions where density increases rapidly from temperature, solid, or both. Buoyancy frequencies in this region can reach 20 cph, less than the highest values recorded in summer, yet still substantial. Hence, despite the warming of surface waters in the 3 Arctic lakes described in section 2b, none of them circulated fully at ice off, and the subsequent development of stratification was rapid. Thus, the lakes did not fully mix following ice off, although the larger lakes does in some years. This pattern differed from that in Lawrence Lake in 1968, although observations of incomplete mixing are reported for other lakes nearby at that time. Incomplete mixing at ice off has been noted in thermokarst thaw lakes, where specific conductance increases near the bottom over the winter from cryoconcentration and respiration in thermokarst thaw lakes in the Mackenzie Delta, Northwest Territories, Canada, whereas more complete mixing is expected in lakes with optically clear ice and minimal stratification from solutes produced over the winter. Human activities, that is, the introduction of salts due to de-icing of roads in winter, are leading to a greater incidence of incomplete mixing in dymictic lakes in the spring. So I think that's going to be, let's see, why don't we do just this section here. Warm monomictic lakes. In warm monomictic lakes, temperatures do not drop below 4 degrees centigrade. These lakes intermittently circulate in the winter or during a cooling season, and they stratify stably in the summer or in a warming season. Warm monomictic lakes are common in warm regions of the temperate zones of the southern and northern hemispheres, particularly those influenced by oceanic climates in mountainous areas of subtropical latitudes and in the lowland tropics, or in northern temperate regions where deep lakes accumulate considerable heat over the summer, and despite cooling in winter, their surface temperatures do not decrease sufficiently to form ice. Warm monomixis is prevalent in many coastal regions of North America and Northern Europe. Examples include Lake Tahoe, and in some years Mono Lake, Lake Constance, Lake Biwa, and Lake Kinneret in Israel. They are found in a tropical region with mixing during a dry, windy season or during a season with clear nights, Lake Victoria in East Africa. So these are, let's see here. So we have figure A, this is from 1970 to 1975. And B from 2004 to 2009 for Lake Kinneret in Israel. So yeah, we're not dealing at all with ice covers whatsoever. This is the month, so this is a full year, a little bit more actually. And these are the depths, so this is about a 40 meters depth. And so you can see the development of the thermocline in the on the month 8, which is 7-8, which is in July, August. And then the absence of any thermocline, so no stratification in the winter as well as the late fall. And similar patterns here, although you can see that there is definitely warmer temperature than there was in the 70s, in the 2000s. You can see a little bit of a peak here, like probably at 28 degrees centigrade, but definitely there is a strong flux of heat during that time. So I'm not sure if this caused by global warming, but definitely it's an anomaly that was not present in the late 20th century. And that's going to be it for today. And thank you for sticking on with me, and we'll see you tomorrow.